Welcome everybody to today's webinar. Today's topic is going to be CFD analysis of vehicle aerodynamics with elements. My name is Dan Combest and I'm one of the managers here at ENGYS. So before we get started, some of the goals of the webinar. Really, I want to introduce ENGYS and some of our innovations. Briefly review the drivers of CFD analysis. I know that there's a variety of people that are on this call, so I wanted to kind of rehash some of that. And then also obtain a sense of how external aerodynamics analysis cases are easily set up within elements. These can be very complex. There can be many surfaces, many boundary conditions, and the intricacies of setting up numerics and turbulence. All of that will cover setting up a simple case or setting up a regular case inside of elements. And then also we'll see two customer success stories. And finally, we'll save questions to the very end. Just a little bit about ENGYS as a company. We are global providers of CFD products and services. We've been around since 2009, and primarily we've focused on enabling open source software in industry. And the suite that we have expertise in is the foam and open foam libraries, which we have done a lot of our own development to create our own specific set of open source CFD libraries and a core called HELIX core. We have 7 offices worldwide: the UK, Germany, Italy, here in the US, Australia, South Africa, and Brazil. And then we also have an established distributor network. So Japan, South Korea, here in the US, France, and Spain. And if you'd like, you can visit our website, engys.com/contact-us, to find somebody that's near you, within your country, within your region. And you can reach out to them and find out more information if you like. The products that ENGYS provides, we have HELIX, which is a general purpose open source CFD software suite. This is used for modeling general problems, conjugate heat transfer, compressible, incompressible. So there's a variety of different problems that HELIX can solve. Elements is specifically focused on the automotive industry, so it's more of a superset of HELIX. Then we also provide HELIX add-ons, and these add-ons are adjoint optimization, block coupled solvers, solvers related to marine hydrodynamics, and then also solvers related to advanced multi-phase flow. Finally, we provide a free graphical user interface for open foam called HELIX OS, and this works with standard open foam. And if you like, you can go visit our website at engys.com/products, and you can find more information about each one of these. All right, so today I want to hit on the drivers of CFD analysis, provide an overview of elements, and then jump into the Aero wizard, which is the set of tools and templates within elements that we can set up an external Aero case. Then I'll briefly talk about method validation, go into customer success stories, and then offer a few conclusions, take-home messages. Okay, so some of the drivers of CFD analysis. One of the main drivers is specifically design improvements. So a product or process is in a design cycle, and we need some sort of performance assessment without actually building this component or putting a vehicle in the wind tunnel. And so it's a virtual performance assessment. Next, one of the other drivers for CFD analysis is what-if analysis. So there's new conditions of a product or process that need to be tested via simulation. So maybe we need to test a specific vehicle in a certain wind condition. We can definitely do something like that. Next would be troubleshooting. So a product or process is performing suboptimally, and engineers, we need to understand why. So rather than, or maybe something might be hard to measure in the wind tunnel or in an experimental setup. So we tend to use CFD analysis to give us more information to help us narrow down possible issues. And then we go on and use experimental methods to verify this or dive deeper. And then finally, gaining insight. So I say engineers and scientists need to understand the structure-function relationship. So structure-function. And this is particularly interesting for external aero because we often want to know the deltas of changing one component out on a vehicle. How will this affect things like lift and drag? And so we have another tool called HELIX Adjoint. And if you attended the last webinar in December, you saw the topology optimization. And I briefly touched on the shape optimization. So this is just a glimpse of some of the technology that ENGYS has to address these different drivers within CFD analysis. So CFD analysis is one step in virtual prototyping. So there's many different components inside of this whole virtual prototyping process. The objectives of CFD analysis are driven by business or knowledge-based needs. We don't necessarily do things, we don't do CFD just for the sake of it. Okay, so if you're in a company and you're trying to get into CFD or bring CFD into your workflow, there needs to be a business need or a knowledge-based need, something like troubleshooting, but it's all tied to a business need. And one important thing is that simulation complexity adds to cost, both time and money. So something that's very simple and you can run on a workstation that has value, that has one cost. But if you need to run on a cluster for weeks at a time or months, then that's another cost. And then also there's a cost with using tools that require a lot of setup. So if you have this really intricate sequence of scripts that you need to run in order to set up a case, then that definitely adds a lot of complexity. So CFD works best when design measurement, when the desired measurement is clearly stated ahead of time. So we could just run and then post-process, but it works much better if you run a CFD simulation with something in mind. For example, I would like to evaluate lift and drag on a vehicle. So that's some of the drivers of CFD analysis, and just kind of take those in mind whenever I talk about elements. Later on, talk about the workflow and talk about why we've actually created this tool. So the origins of Elements. Elements was actually a joint venture between the Auto Research Center here in the US, who are experts in automotive engineering, research and development. They have a wind tunnel, they help customers build wind tunnels, and they have lots of experimental setups, and they're also experts in running CFD simulation. And ENGYS. So ENGYS, we are open source CAE software engineering developers. We work in CFD, we work in multidisciplinary design optimization, development, and support. And a company called Streamline Solutions was created. And this combination of expertise allows us to be able to create a tool and also work with industry experts like Auto Research Center to bring the best possible tool to the automotive industry. So the vision of Elements, it is a vehicle design and analysis suite meant to satisfy the needs of different groups within a company. There's an advanced graphical user interface, which makes setting up cases very easy to use. And there's embedded best practices for best-in-class vehicle design simulation. So the best practices, which I'll talk about a little bit more in the validation section of this discussion today. There's also user support and extensive user written documentation. And the way that things are created, the way that the program is written, is that it's a modular architecture for fast expansion and development. And all of this is based on an open source simulation engine. What does that mean for companies? It means that there's no parallel licensing for things like I run one simulation on 1,000 cores. If I want to run 10 simulations on 1,000 cores all at the same time, then there's no parallel licensing on the backend component. So meshing, simulation, those aspects. The only time a license is ever checked out with Elements is when the graphical user interface is open or when client server architecture is being used to run a remote simulation. And I'll talk a little bit about that during the demonstration. So within the Elements package, there's a general CFD GUI. So something like exactly like HELIX. So you can do general CFD conjugate heat transfer, compressible, incompressible, multi-phase cases. And then also there's an Aero wizard, which allows you to set up these external aerodynamics cases. Again, all of this is over top of the HELIX core, which is an open source CFD simulation engine. And with this entire framework, we're able to add additional things, which are elements add-ons, so solver extensions for things like adjoint, coupled, things like that. And with elements, there's user support, code maintenance with regular software updates, bug fixes, things like that, and then documentation to allow you to do self-study, to dive deeper into the different settings of the mesher. If you're setting up a lot of things via text files after you've set up a case and you want to go through and tweak something on the back end, you can do this kind of thing using the documentation that comes with elements. All right, so let me talk about the Aero Wizard. The Aero Wizard is a GUI that guides the user through several different steps. It's a virtual wind tunnel type approach, so we can do virtual wind tunnel simulations. There's 7 simulation steps, so we choose a body type, we choose a vehicle geometry, we set up the wheels, we set up porous media, we set up anything within the wind tunnel, and then we run the case. The whole process is an automatic CFD mesh and DES setup for different vehicle shapes and configurations, and you'll see exactly what I'm talking about here in a moment. And this uses a validated DES method as the default method. Sure, you can change your turbulence model if you like. If you'd like to use RANs, you can definitely do something like that. Or if you want to try a different DES model or DDES model, you can definitely do that as well. So this leads me to the point of it's fully customizable. You can embed your own simulation best practices within the GUI. And again, it's an open source simulation engine. So let me do a quick demonstration. And today I'll be working with a drive-air SUV. So this SUV was actually created by Thomas Schumacher here in ENGYS. And this is from the drive-air model. The model was created from the drive-air model geometry. All we need is the geometry, porous media, parameters, and then a test velocity. So let me go directly over to elements. So when we start elements, we're met with this client server connection start. And what client server is it's a technology to allow users to connect to different computing resources. So for example, I'm going to connect locally to a local host. If I had this set up, I could connect to a workstation back in my office. I could connect to a cluster that's on our own premises. I could connect to a cluster that might be a cloud resource. So I can add each one of these different servers or different connections and different resources via this server connection wizard. So today, I'm just going to be running on a local host to connect and set up a case. Okay, so when we start, we're met with some of the most recent cases that I've been running, and then we could also open another case that's maybe saved in a different location, or we could start a new case. Let's start a new case. And here, let me save the case in a particular parent folder. We'll leave this as the default. And let's call this Drive Air SUV. And let's do it on 256 cores. So let me set it to 256. So this is going to be run in parallel. Let me hit OK. So immediately we're met with the general CFD interface, and the general CFD interface has a mesh, setup, solver, and view tab. However, we'd like to use the external Aero wizard. So let's come over here in the ribbon interface to external Aero, and let me click that button. And what that will do is we'll start out and the user has to choose a set of configuration files. So these are the templates, these are the best practices. Right here, these are the defaults. So in theory, it's very easy. Actually, it is very easy to add different configuration files based on different groups. So, or different years or different models or different wind tunnels, whichever you like, however you like to group this. If there's a rolling road or if there's a specific wind tunnel geometry that you want to make sure that you're including with each simulation, then I can have different configurations and those will appear in this window right here. So let me just select the defaults and then go to body type. And again, we've broken up body type into coupe, hatchback, SUV, pickup, sedan, squareback, truck, stock car. We could go even further and we could do things like a sedan with rotating wheels in a dynamic mesh type case, or we could do a sedan with a multiple reference frame for wheels, or we could do particular models. So if you had a set of best practices that you'd like to apply to a particular model, then you can definitely set up one of those. You can set that up directly in here. We can customize this icon shape, or sorry, the icon color. So I can actually put a picture here if I want. Today, let's just choose SUV, and then we'll go to vehicle geometry. Next, I need to import the geometry. And let me go ahead and select all of this and hit open. So here we've got our geometry, and over here we've got a list of the different geometry components, so the different assembly types. And you can see that these are already broken up into different subsections. So we've got body, engine bay, porous media, underfloor, wheels, and then we've got our wheels broken up into their specific location. Each one of these groupings of vehicle geometry, they're called assembly types. And by default, when everything's brought into to elements, everything's a body, type body. However, if you prepend the STL file with a particular keyword, then you will actually be able to go ahead and separate each one of these into the different assembly types automatically. So you won't have to. It saves you just a little bit of time if you like to do that kind of thing. These assembly names right here, these are completely customizable. We can add assembly types if we like. If you don't like underfloor and you want to call this underbody, we can change to this. You can change the wording, the color. And what this does is that each one of these different assembly types are treated differently within the CFD simulation. So for example, the number of layers on the body assembly type is different than the number of layers that would be added to the underfloor assembly. So each one of and then also the boundary conditions would be different. So the boundary conditions on wheels are different than the boundary conditions on body. And then porous media, this actually adds a porous media model to the simulation. Okay, so within this whole process, first we import the geometry, then we need to go through and do a few additional things. So we don't need to do anything for each one of these different body components. We do, however, need to come through and set up the porous media. The porous media, we can use a tool to figure out and to detect exactly what the orientation of this porous media is. So if we have a radiator that's at an angle and we need to change these local coordinate system vectors of this porous media, we can do that very easily. We can hit reset and try to have it estimate or try to sense exactly what the orientation is. Then what we can do is set up the porous media coefficients. Depending on what the units are for your different porous media coefficients, we can select different models, and then these will be converted back to what elements needs to run the simulation. And then also there is a pressure drop curve, so we can supply velocity versus pressure drop and then use this. The GUI will be able to extract the viscous and inertial loss coefficients from that particular curve. All right, so if we want, we can go ahead and set these different porous media coefficients. So we've got 3 to the 7 and 400. Next, we don't need to do anything for underfloor. And then for wheels, so these are going to be wheels that the rotational motion is approximated with a rotating wall boundary condition. So the wheels, the mesh is going to be static, but we're going to be providing a rotating wheel boundary condition. And for that, we need to know the center of rotation and the axis of rotation. We could use this reset button to go ahead and sense each one of these. If we wanted to also, we can use this wheel widget, And what this does is this allows us to go through and select different points on the wheel itself to help determine this rotating axis. So this is specifically designed for situations where you might have toe or camber on a wheel, and it makes it very difficult to find this center of rotation and axis. And so all we would do is we would select 3 different points. You go back and select that first one again. And then this will change the location of this center of rotation and axis of rotation. And then once we're ready to go, if we'd like, we can just hit save. I hit reset because there's no toe or camber on each one of these. Okay, so we can do that for each one of these wheels. For this particular case, it's relatively straightforward. It's already been sensed for all of the different wheels. So we can go through and just check and make sure that these orientation vectors are in the approximate location. Okay, so we're good with that. Next is the wind tunnel, and we can set a yaw angle at this point. We can notice right now that the floor of the wind tunnel is hitting in the middle of the wheel, so we can adjust the floor height. So now it's been moved down below the wheel, so that did that automatically. Next, we can move to run settings. Here's where we can set the test velocity. We can use a tool to estimate the frontal area. If I know what the frontal area is, I can go ahead and enter that. We'll need the wheelbase for the moment calculation. And this checkbox right here, if we have this checked, the GUI will automatically generate a report, and I'll show an example of that report here in a minute. Within that report, there's different images, there's different summaries of how long the simulation took, what the mesh size was, how many cores, where's the, what geometric components were there, where is this case on the cluster. And then finally, if you have access to the adjoint module, then we can run adjoint and determine the sensitivities to minimize lift, to minimize drag, and to minimize rear lift automatically. And so what that'll do is that will give us a map of the surface sensitivities on the vehicle. For this case, I don't necessarily need that. All right, so if I'm ready to go, I'll hit apply settings. Okay, so we've brought in our different components, we've categorized the assembly, we've provided the test velocity and the porous media coefficients, and from there, the GUI was able to go through and automatically set up all the different wake boxes, set up all the different refinements. So for example, for a body component, for this case, it's going to set a level 7/8 with a base mesh spacing that is around 0.63. Now, each one of these, this base mesh spacing is based on a best practice. It's based on fraction of a characteristic length within the simulation, and then everything is related to that. So it sets our surface refinements, it sets distance-based volume refinements. It also automatically sets the different layer settings for each one of these different components. Now, for this case, there's not a lot of geometry for the actual vehicle. However, if you have a case where you have hundreds or several thousand, and sometimes people do have that kind of scenario, this speeds up the whole setup and a tremendous amount. So we've got all of our mesh settings, and for the setup, we've got our different solution states, so it automatically sets up what type of physics we have. So for this case, we're doing segregated, transient, incompressible, and the material that we're using is air, and the modeling approach that we're using is a DDES Spallard-Almaras. So we've already set up all of the different boundary conditions for the wheels themselves. We've automatically detected that rotational axis and the origin of rotation and the hub speed, so things like that. Also, we've set up in situ data calculation, so we're able to do things like averaging of a transient field, so we'll get average CPs or pressure or velocity, and then also set up things like our lift drag function object to determine what the lift and the drag is on the vehicle. And then finally, field initialization. And this will initialize with potential flow, but then it'll progress within the transient run from there. So let me just save it again. And then kind of show you an example of what it's written. So here we've already set up all of our different processor directories. We've set up our constant and system directories. And so everything that we need to actually run this case on the cluster is already there. All right, so let me jump back to the presentation. And this particular case, we ran with about 56 million cells. It took about 8.87 hours on 128 cores. I would say that this is, users typically have meshes between 40 million and 250 million, depending on the vehicle type. For an SUV, you could definitely go for a multiple of 56 million cells, 8.87 hours on 128 cores. That's a very quick run. And I would say there's plenty of time or plenty of resources to run a case on either fewer cores and we can run more cases, or we could go back and we could adjust the mesh and we could run the case with a smaller mesh for the same amount of cores and give it a little bit more time. Most customers target having a case turnaround within 24 hours. And within this, the output from the simulation is transient and average field data. There's lift and drag data. There's images of CP, streamlines, near wall velocities, isosurfaces, slices along the geometry. So let me just show an example of the report. So you're given a docx and a Word document and then also a PDF. Now all of this is completely customizable. All of these images were done through Elements, and so they're set up through a post-processing script, which is also very customizable. So if you don't like the angle or you don't like the color scheme or you'd like to have more images in order to make animations, you can do that completely. It's completely customizable. And many companies do that for each one of their different vehicles or different teams. All right, so again, let me jump back. So some important points. The auto interface is efficient and easy to use. It enables many cases to be set up very quickly. I even walked through this and spoke, and it just took a few minutes. If you're determined and you really need to set up a case very quickly, the most time-consuming part is importing the geometry and categorizing, and then you just hit apply and save, and you're ready to go. So the methodology uses templates. Companies can develop their own best practices and share them within organizations. The important thing is that there's consistency among users. So this is ideal for local and remote teams. And it's very easy for one engineer, one group of engineers to set up templates and share them with each other or share them with another team. You can also do specialized setups with multiple reference frame or sliding mesh for the wheel motion. This also uses a validated approach. So we validated the results against the wind tunnel data thanks to ARC, thanks to the Auto Research Center. And then clients have shown that this approach is repeatable and in good agreement with their own wind tunnel data. So let me talk about that methodology. We've talked about the GUI, we've talked about the motivation. Let's talk about the wind tunnel validation effort. The overall objective was to validate the best practices for external aerodynamics CFD. The requirements were wind tunnel measurements from the Auto Research Center and other OEM wind tunnel data. There's a wide range of vehicle shapes. And the outcome of this was to be able to provide information for an automatic CFD process. How do we develop these templates? And what kind of information is useful when we create these different templates? We wanted consistent drag prediction across multiple vehicle shapes. And then we wanted to be able to provide a solution that had high accuracy within a specific level of error. There was a paper written a few years ago called A New Aerodynamics Analysis Software in the International Journal of Automotive Engineering in 2014. If you'd like to search for that, and if you have questions on that, you can always email us and we're happy to answer. So some of the vehicle types during this validation effort: sedan, hatchback, estate, SUV, streamliner, NASCAR, IndyCar, light duty truck, heavy duty truck. So it's a wide range of vehicle shapes. There were over 200 test configurations on all of these different vehicle types. There was fixed ground, various levels of moving ground, different test speeds, different yaw angles, different ride heights, and different vehicle modifications, so closed versus open cooling, spoiler on and off, if there was a underbody panel included or excluded. So there was a wide variety of deltas within this test matrix to give us a really good picture. So if we're looking at the test matrix for vehicles, and there's a variety of mesh sizes from under 30 million to over 100 million in this test matrix. The average error magnitude for drag was about 1.2%. For front lift, it was about 9.37%, and for rear lift, it was the average error magnitude was 9.24%. For trucks, on the other hand, the average error magnitude was about 2.5%, front lift was 3.1%, and rear lift was about 14.4%. So let me talk about some customer success stories. The first one I'd like to talk about is from Volvo. So Volvo performed a CFD benchmark in which they compared wind tunnel data versus CFD codes, various CFD codes versus elements. And there were multiple configurations tested on 3 different vehicles, so V60, S60, and XC90, so a sedan, an SUV, and then so each one of these, there were different configurations with open cooling or closed cooling, and with wheel deflectors or rim covers. So there was a variety of test conditions. And again, this was actually written in a paper and shared via JSAE Annual Congress a few years ago. So there was the name of the paper is a CFD benchmark for improved accuracy of aerodynamic simulations, and this was done in 2017. Just some information about the wind tunnel. They wanted to get results for on-road conditions. It's a moving belt. There was also boundary layer control, and for this case, the test velocity was 140 kilometers per hour at 0 degrees yaw. So for the CFD setup, it used the automatic hex dominant parallel meshing that is used within elements, and it used the best practices for external aero, transient incompressible flow analysis using a delayed detached eddy simulation, specifically the Spolart-Almaraz turbulence model. The velocity was 140 kilometers per hour at 0 degrees yaw for each one of these cases. And there was condenser, radiator, intercoolers, and each one of those were approximated using or modeled with the Darcy-Forsheimer model. There were cooling fans with rotating wall velocity on each one of these fans, the moving ground with rotating wheels, and the wheels, their boundary conditions were the rotating wheel boundary conditions. So the mesh is static, there's no MRF, it's just a boundary condition on the wheel itself. And all of these simulations were cold flow, so we ignored the thermal effects. So if you look at the V60 and we're looking at CDA, so drag coefficient, and in this sequence of results, we're comparing the baseline, which is this red line right here, and we're comparing the baseline wind tunnel data versus different setups or different configurations for the V60. Okay, so we can see right here that this green line, code 5, which is elements, also agreed well with the baseline results, with the wind tunnel results. So it agreed well in terms of magnitude and also in terms of trend. So when a delta went up over the baseline, Elements also predicted that, and it was also a similar magnitude. Let's also look at CDA for the S60. Again, the red line is the experimental results, and then the green line, which is code 5, is also elements. So again, we can see fairly good, agreement with the trend of the deltas, and then we can also see very good agreement in terms of the magnitude of the deltas. Let's talk about the XC90. Again, the red line is the baseline, and the green line is code 5, which is elements. We can see identical changes in terms of the direction of the deltas, and then the magnitude of the changes is very accurate compared to some of the other codes, so code 4 specifically. Here we look at the rear lift for the V60, and again, the red line is also the experimental results, and the green line is elements. And these other codes, we've got code 3, code 4, and code 2. So code 5, again, it matched the direction of the deltas. The magnitude was still very close for the rear lift for the V60. And if we look at the rear lift for the S60, we can also see, again, the trend was predicted correctly. The magnitude of this trend was a little bit off in terms of code 5, but with respect to the other codes, specifically code 4, it was a greater magnitude, and also that was a similar trend. For the XC90, again, we see the red line, which is the baseline, which is the experimental results, and for the green line, which is code 5, we see that it also predicted the correct trend. It was also closest to the experimental results compared to the other codes. So overall, just some notes, this CFD benchmark was performed by Volvo, and they wanted to compare the wind tunnel results with different CFD codes. There was multiple configurations tested. Overall, the results agreed very well, specifically with the direction of the deltas, and the magnitude of the deltas was on point for most cases. Volvo ended up selecting multiple codes, so code 4 and elements within their company. And so overall, this was a great benchmark comparing different vehicle types with different configurations with wind tunnel data that perform very well. So the next one is from CRF Fiat, and this was over the Fiat Bravo. This used a DES transient aerodynamics analysis, and this was also performed in elements. It was an open cooling geometry, open road conditions, and the goal was to verify the best CFD simulation practices for accurate prediction of lift and drag. They compared the wind tunnel and CFD results of various commercial codes. In these slides, I am not showing the CFD codes because I don't have those results. So we're only going to show just elements versus the wind tunnel results. So for this particular case, again, it used the automatic hex dominant parallel meshing that's with the embedded best practices for external aero. For this particular case, there was lots of geometry in the underhood location. There was localized volume refinements to resolve wake and other important areas. And there's near wall layers to model boundary layer flow. So those 2 points right there, that's consistent in every one of these best practices for every vehicle type. There's always layers on specific components. There's always volume refinement boxes. These are scaled to different sizes based on the vehicle size and type. And then there's also zonal meshing to capture porous media. And for this case, the simulation was also a transient incompressible flow analysis with the delayed detached eddy simulation, specifically the Spillard-Almaraz, again at 140 kilometers per hour. There were several porous media present in this simulation for a condenser, a radiator, and intercooler. And the moving ground, so the rotating wheels was again approximated with a rotating wall boundary condition, so the mesh was static, but the wheels themselves had a boundary condition set on the wheels. This was also a cold flow simulation. So just a peek at some of the underhood velocities. This was one of the components or one of the areas that was important to this customer, and they wanted to make sure that they were capturing the different underhood velocities within the different porous media and around the engine. If we compare the drag coefficient and the lift coefficient with the experimental results, so if we normalize that, we were within 2.6%. Elements was within 2.6% for the drag and within 16% of the lift. And again, this is a normalized value. So 1.02 was a normalized value compared to the wind tunnel data. Okay, so some conclusions, some take-home messages. So the approach used in Elements agrees well with customer supplied experimental results. It also agreed well with the test matrix that have over 200 different configurations on many different vehicle shapes and types that were performed by the Auto Research Center. And the success for the customer success stories, so that was a combined effort of the customer engineers, the technical support, the GUI, the training that users received in order to use the GUI properly, and then also the documentation. So the best practices are fully customizable. You can do steady, transient simulations. You can adjust the turbulence model. You can adjust the wheel treatment. I just did a rotating wall wheel. We could do MRF if we had grooves, or if we wanted to approximate wheel motion by using a dynamic mesh approach where certain components of the wheels are rotating, we can definitely do that. We can adjust the meshing parameters. So if we want to have more layers, or if we want to have smaller cells or different refinements, we can definitely do that. We can adjust our data output. And then most importantly, beyond the accuracy and beyond the numerics, beyond the settings, if we want to be able to extract the information and build a report to summarize everything, we can customize how results are post-processed, and we can customize this report content and structure and appearance. So if you have to give a report to a manager, or you have a weekly team meeting where you need to share your results, it's very easy to do that kind of customization. So lastly, why Elements? Elements is an enterprise CFD solution. It has minimal CAD cleanup. That's one thing I didn't really hit, but the way that the mesher is written, the way that the mesher was developed, is that it requires very little CAD cleanup. So we don't have to spend a lot of time if a new component was created to send it off to another team to do much CAD cleanup. It doesn't need to be watertight. And basically with CAD and the mesher, if there's a feature that's smaller than the cell size itself, then that feature will be, it won't appear within the mesh. And then also it uses an advanced automatic parallel mesher. So it's very easy to set up meshing scenarios. So also, if you're doing other types of simulations, it's very easy to set up these different meshing parameters. It's fully validated. It's highly accurate. It's WLTP compliant. It uses open source solvers that are scalable, fast, and efficient. It's very easy to learn and use. It's multi-platform for both Linux and Windows, and there's best-in-class user support from both ENGYS and the Auto Research Center. Finally, it's cost-effective. Just some upcoming events. There's another webinar, and that one will dive into more detail about meshing. And another important event that's happening here in the US is the 15th OpenFOAM workshop. If you're in the OpenFOAM world and you want to submit an abstract, those abstracts are due January 31st of 2020. That was extended. If you'd like to see more events, that we're part of, you can go to engys.com/events. You'll see our webinars. You'll see the different conferences that we'll be at if you want to try to meet one of the people in ENGYS to talk in more detail about your cases.